When you type Docker run and hit enter, something fascinating happens. A new world springs into existence. It has its own file system, its own network, its own process tree. But here's the thing, it's not a virtual machine. There's no hypervisor, no guest operating system. If you look at it from the host, it's just a regular Linux process. You can find it with ps-aux, sitting right there alongside everything else. So what creates this illusion of isolation? How does a single process think it has an entire machine to itself? The answer lies in 3 elegant kernel features. And once you understand them, you'll never look at containers the same way again. Let's look at this from both sides. From inside the container, you see a fresh Linux system. Your process is PID1. You have your own root file system with bin, usr, and etc. directories. You have your own network interface called eth0. But step outside to the host. That same process has a completely different PID, maybe 4521. The file system it sees is actually just a directory on the host's disk. And its eth0 is actually one end of a virtual network pipe. Everything the container experiences is an illusion carefully constructed by the Linux kernel. 3 mechanisms make this work. Namespaces control what a process can see. Cgroups control what resources it can use. And union file systems handle storage efficiently. Let's examine each one. The Linux kernel gives us 3 powerful tools for building containers. First, namespaces. These control visibility. A namespace wraps a global system resource and makes it appear to processes inside that namespace as if they have their own isolated instance. Think of it as, what can this process see? Second, Cgroups, short for control groups. These control resource usage. They let you set limits on CPU, memory, disk I/O, and network bandwidth. Think of it as, what can this process use? Third, union file systems. These provide efficient, layered storage. They let multiple containers share the same base image while keeping their own changes separate. Think of it as, how does this process store data? Together, these 3 features transform an ordinary process into what we call a container. Let's start with the most intuitive namespace, the PID namespace. On a normal Linux system, every process gets a unique process ID. PID1 is special. It's the init process, the ancestor of all other processes. When Docker creates a container, it uses a system call called clone with the clone_new_PID flag. This creates a brand new PID namespace. The first process in this new namespace gets PID1. From inside the container, it looks like the init process. It thinks it's the very first process on the system. But from the host's perspective, this same process might be PID 4521. It's just another process in the host's process tree. It's like having 2 name badges. Inside the container, your badge says number 1. Outside, your badge says number 4521. Same person, different contexts. The kernel keeps track of both. PID isn't the only namespace. The network namespace is equally important. Each container gets its own complete network stack, its own interfaces, routing tables, and firewall rules, but it still needs to communicate with the outside world. Docker solves this with virtual Ethernet pairs. Think of a VETH pair as a virtual network cable. One end sits inside the container as eth0. The other end connects to a bridge on the host called Docker 0. Packets flow through this pipe in both directions. Then there's the mount namespace. This isolates the file system view. The container sees its own root file system, its own /directory. But on the host, this is just a directory somewhere on disk. Linux actually has 6 namespace types in total. Besides PID, net, and MNT, there's UTS for hostname, IPC for interprocess communication, and user for user IDs. But PID, net, and MNT are the 3 you feel most when working with containers. Namespaces handle what a process can see, but what about what it can use? Without any limits, a process inside a container could consume all the CPU and memory on the host machine. It could starve every other container and the host itself. This is where Cgroups come in. Cgroups, or control groups, let you set hard limits on resources. You can say, this container gets at most 2 CPU cores and 512 megabytes of RAM. When you run Docker run with -- memory 512M, Docker creates a cgroup for your container and writes the limit to a file at sysfs cgroup docker, followed by the container ID. If the container tries to allocate more memory than its limit allows, the kernel's OOM killer steps in and terminates the process. No negotiation. Cgroups also handle CPU shares, disk I/O bandwidth, and even the number of processes a container can create. They're the guardrails that keep containers from interfering with each other. Now let's talk about how containers handle storage. A Docker image isn't a single file. It's a stack of read-only layers. When you write from Ubuntu in a Docker file, that base image becomes your bottom layer. Each subsequent instruction, like run apt install or copy your application code, adds a new layer on top. When a container starts, Docker adds one thin writable layer at the very top. This is the container's scratch space. Here's the clever part. If the container needs to read a file, the file system searches from the top layer down until it finds the file. But if the container needs to modify a file from a lower layer, it first copies that file up to the writable layer. Then the modification happens there. This is called copy on write. The original lower layers remain untouched, and this means something powerful. 10 containers running from the same image share all those read-only layers on disk. Only their individual writable layers are unique. This saves enormous amounts of storage. Now we can see the complete picture. Let's walk through what happens when you type Docker run step by step. First, Docker checks if the image layers are already cached on your machine. If not, it pulls them from a registry like Docker Hub, layer by layer. Next, it creates a new writable overlay layer on top of the image. This is the container's file system using OverlayFS. Then it creates all the namespaces, a new PID namespace so the process gets its own process tree, a new net namespace with its own network stack, a new MNT namespace for the isolated file system view, plus UTS, IPC, and user namespaces. Docker configures Cgroups with whatever resource limits you specified, like memory and CPU constraints. It creates a virtual Ethernet pair, connecting one end inside the container and the other to the Docker 0 bridge on the host. And finally, it executes your entry point process inside this carefully constructed sandbox. That process becomes PID1 in the container. And just like that, you have a running container. So how are containers different from virtual machines? The distinction is fundamental. A virtual machine runs a complete guest operating system with its own kernel. Between the hardware and the guest OS sits a hypervisor that emulates hardware. Each VM carries the full weight of an operating system. That means gigabytes of memory overhead and seconds to boot. A container shares the host's kernel. There is no guest OS, no hypervisor. It's just a process with namespaces and Cgroups applied. That means it starts in milliseconds and uses megabytes, not gigabytes. But the trade-off is isolation strength. A VM has a very strong security boundary because the hypervisor separates guest and host kernels completely. A container shares the kernel. If there's a kernel vulnerability, the container boundary can be breached. Neither is universally better. VMs offer stronger isolation. Containers offer speed and density. Many production systems use both, running containers inside VMs to get the benefits of each. Sharing the host kernel is efficient, but it comes with risk. A kernel exploit inside a container could potentially affect the entire host. That's why Docker doesn't rely on namespaces and Cgroups alone. Linux capabilities break root privileges into smaller pieces. Instead of giving a container full root access, Docker drops dangerous capabilities like the ability to load kernel modules or modify the network configuration of the host. Seccomp profiles restrict which system calls a container can make. Docker's default profile blocks around 44 of the 300+ system calls, including ones that could be used for privilege escalation. And mandatory access control systems like AppArmor and SE Linux add another layer, confining what files and resources each container can access. Today, orchestrators like Kubernetes manage thousands of these containers across clusters of machines. But at the very core, every single one is still just a process, isolated by namespaces, limited by Cgroups, stored in layers. Now you know what's really happening when you type Docker run.